Welcome to The Exchange. I'm Dan Riley. The Exchange is a streaming internet talk show and podcast of interviews with noteworthy people about their lives, ideas, and current events. This week I sit down with NASA research scientist Jack Lissauer. During our conversation, Jack talks about his path to working at NASA, the process by which stars and planets are created in the universe, and his work on the Kepler program, which is trying to discover Earth-like planets that are orbiting other stars. All right, Jack. Well, thank you so much for taking some time to come onto the show, and welcome to The Exchange.
My pleasure, Dan. Like talking about these things, and I think you have a great format here.
Thank you. I appreciate that. Would love to start by kind of learning about your background. I know you work in space and work for NASA. Were you always interested in science and astronomy and space generally, or was that something that you sort of acquired later in your academic career?
Well, I grew up in the early part of the space age, and I don't remember Project Mercury, but I do remember Gemini and certainly Apollo very well. And I was very interested as a child in mathematics. And when I went to college, I was considering majoring in math, physics, or economics. And I basically decided against economics and went right along the math-physics pathway throughout school. I actually have my degrees in math, but even though my doctorate is in applied mathematics, my dissertation was Saturn's rings.
And now you work for NASA. I would be curious to know sort of the story of one's trajectory from being interested in majoring in math and science to actually getting to the point where you're working for NASA. Was that always a goal of yours? And how did you kind of make that work?
Well, it was a random walk, or a pseudo-random walk, perhaps. When I was an undergrad, I took a course on the planets in our solar system. And I had been interested in planets since learning about them in a module in first grade, but I never thought of it as a career. And even when I went to grad school, I didn't think of it as a career. I took the course as an undergrad because I was considering academics, and my advisor said you should take courses from inspired professors, and one of the ones on the list that he gave me was Erwin Shapiro, who team taught a course on planets, and I liked it, so I took both semesters of it, my last 2 semesters in college. I came out to Berkeley to do PhD, math, physics, and I found myself uninterested in most of the things in the math and physics department. And a student who was taking a astrophysics seminar with me suggested I meet some of the theorists in the astronomy department. And I met 2, and one I got along with very well. The other I liked too, but one I got along with even better. And we started working together. And he had friends who worked at NASA Ames. And some of these people did planetary things, or they were connected with people who did planetary things. He sent another student of his who didn't have a supported and well-defined PhD project down there to meet these people. I went along for the ride because I was interested in planets, and it developed from there.
So we're obviously sitting on a planet. I'm curious to know what is it about planets that fascinated you, and what is the story of the creation of our own planet and planets generally from a scientific perspective?
Well, as you say, we live on a planet, so it's a part of the universe that is relatable, but it's also out there. And that type of connection just appealed to me. Now, in terms of planet formation, the way stars form is from the collapse of a gas and dust cloud, or more specifically, a condensed or a relatively thick core within that cloud. And it collapses from something that is a light year or so in size down to a star, which is less than a 10,000th the size. And because of that, just as when a dancer who's spinning brings her arms closer to her, she spins more rapidly. And you can see this even more graphically when you see astronauts do this on the space station. The cloud will spin up much faster, and in fact, it will spin up by a factor, in that case, of 100 million. And even though these things are spinning slowly, you spin up that much, you're whirling about, and the centrifugal force will toss you out. So it can't be that compact. And material wants to fall in. That's what gravity wants to do. But this angular momentum forces things not to go all to the center, but the lowest energy state, the closest to the center it can get, while still having this spin, this angular momentum, is the central condensation, which becomes a star, and a disk surrounding it. And in that disk, some of the material falls into the star, some stays out. The dust agglomerates into bodies called planetesimals. They collide to form planets like our own. And the bigger planets, the Jovian planets, which are mostly hydrogen and helium, which are too volatile to be anything other than gaseous at any realistic temperatures that the solar system could have formed at, they make up over 98% of the sun and of this disk. And once a solid planet gets massive enough, several times the mass of the Earth, then it can start gravitationally attracting those gases.
So in terms of just the uniqueness of the sort of planet that we're living on right now, I know that's one of your areas of research and expertise. How long have we known that first of all, that the process that you were just describing, that is the way that planets actually come into existence? I mean, for almost all of human existence, I would imagine we've been completely ignorant of how planets actually form. How long have we known this information?
Well, there are a few aspects of planet formation. One is the formation of planets within a disk around the sun. And that actually goes back to two of the great thinkers of the 18th century. Immanuel Kant, best known as a philosopher, but this was natural philosophy, and he came up with these basic ideas in the middle of the 18th century. Towards the end of the 18th century, Pierre-Simon de Laplace, French mathematician, who wasn't aware of Kant's work, actually came up with similar ideas, but he placed them on a much sounder mathematical footing. However, the growth within the disk, starting with planetesimals growing up, wasn't part of their ideas. And in fact, that came on towards the end of the 19th century from an American geologist named T.C. Chamberlain, T.C. Chamberlain, and who thought that there wasn't a disk, thought that just something came by the sun, another star, or maybe a comet, and tidally moved material, and then it formed, which was discredited. And the first people to really put things together to get the big picture that we have today are O.J. Schmidt and Viktor Sergeyevich Safronov in the Soviet Union. Schmidt worked in the 40s and 50s. Safronov worked with Schmidt in the 50s. And then into the 60s, 70s, 80s, when I met him, and 90s, I worked with him a little bit.
So here we are. We're just beginning the 21st century, and we now have some technology that will allow us to consider the possibility, or at least begin to investigate whether there might be other planets similar to Earth out there in the universe. And that's one of your areas of expertise. My understanding is that investigation is primarily being done through the Kepler program. How did you get involved in Kepler? And if you could describe briefly what Kepler is, that would be helpful too.
So Kepler is a spacecraft that orbits the sun a little behind Earth, a little slower than Earth, so it gradually drifts behind. And it looks out at one area of the sky, and it looked at that area for 4 years, almost continuously, measuring the brightness of over 160,000 stars every 30 minutes. And the reason it measured so many stars all the time was because it was looking for little dips that occur when a planet goes between us and its star and blocks a little bit of the star's light. Now, most planets won't go between us and their star. We have to be looking at the system, the planet's orbit, nearly edge on. And therefore, only, for instance, 1 in 200 observers randomly placed in the sky would see Earth going in front of our sun. Therefore, you need to look at a lot of stars to get a good sample of transiting planets. This is the partial eclipse the planet makes when it goes in front of its star is referred to as a transit. Now, stars vary in brightness. There are star spots, there are flares, things like that we know from our sun and that are more common in some of the other types of stars. But the thing about transits is that they're very periodic. They occur once every orbit of a planet, which is essentially constant. If you have multiple planets, they can pull each other a little bit forward and a little bit back, but that changes the period only very slightly. Now, Kepler is, as you mentioned, the technique, the transit technique with the Kepler spacecraft is finding the objects closest to that of our Earth. You can do transits, and people do, from telescopes on the ground, but the ground, first of all, there's a day-night cycle. Then the weather can be bad, and also the atmosphere is not completely clear. So because of that, you can't see very small transits. The Earth blocks less than 1 part in 10,000 of the sun's light seen by a distant observer. And also, you can't see reliably long period transits because you'd have to be really lucky to know when they're occurring and to get them. So from space is better. Kepler is by far the largest telescope that's been ever launched with a wide enough field of view to look at many moderately bright stars. And therefore, it's been by far the most successful at finding planets somewhat like our Earth.
And is your job on a day-to-day basis to look solely for Earth-like planets, or is it just to sort of take in all of the information that Kepler is bringing to us and draw some conclusions from that information?
My job is to take in the general information and draw conclusions, and especially about typical characteristics of planetary systems, the relative periods of planets in systems where we see more than one planet transiting, and how this relates to our understanding of planet formation. Because, although I mentioned earlier, we're confident in our general picture of planetary growth as a result of 3 centuries of research. The particulars are complicated and ill understood.
So where are we now with kind of what we've learned about the potential for other Earth-like planets out there in the universe? Have we been able to identify any that are very probable in that characteristic or not?
We're getting close. We found planets that are the size of Earth and even smaller, but they are very hot because they're very close to their stars. We found a few planets that are only a little larger than Earth that are getting about as much energy from their stars as we get from our sun. Although their stars are a little different from our sun because they're a little cooler. And the reason the cooler stars help is because these stars are smaller, they're cooler, most cases, and therefore they're significantly less luminous. The planet's going to be closer to its star. It's going to be larger relative to its star, so it'll block a larger fraction of the light. Because it's closer, it will come by more often, and also the chance that we're seeing it because it's going across a face of its star from our vantage point is going to be larger. The other thing that we found with the Kepler spacecraft is that in order to have a planet like Earth, you don't just want it to be our size and our amount of energy, but you want it to be a rocky world. We look in our solar system, people often call Earth the water planet because it's mostly covered with water, but it's really less than 1/10 of 1% water. And even for ocean-dwelling life, being near a rocky surface is very important for things to be chemically inhomogeneous, to be able to get the energy and the elements necessary for life to survive, and probably even more so, surface may be necessary to get the disequilibrium necessary for life to form.
If we get to in thinking about the future and the sort of more information that Kepler may provide us, and with additional research that might be done with other missions, how do you think the next sort of 10 or 20 years or even further in the future will look in terms of the more information that we'll learn, the more science that we'll know about how many Earth-like planets there may be in the universe?
Well, that's a very good question, and I could spend an hour answering it, but I'll try and be a little briefer. In terms of finding how many planets there are, Earth size around in the right distance from their stars, Kepler data will be analyzed more, and we're going to get a better idea, but we're probably not going to see many, if any, planets that are only 1 Earth radius that are at the 1 Earth-Sun distance from a Sun-like star, so a true Earth analog. Therefore, from Kepler data, we're going to have to extrapolate. And Kepler is actually probably going to give us the best data for at least 10 years. The Europeans will launch a Kepler-like spacecraft in about 2024, and it actually won't look at one area for as long as Kepler does. So it by itself won't get better information. But part of the time, it will be looking at the area Kepler did. And you can look at those two sets of data together, and that will give us a better idea on Earth-sized planets at Earth-like distances from Sun-like stars. But the question is, how different can you get in size and other properties to be Earth-like? Now, in 2017, NASA plans to launch a smaller spacecraft that will do a survey of almost all the sky called TESS. It's the same principle as Kepler, but it's a much smaller telescope with a wider set of cameras, wider lens cameras, and it will point in different parts of the sky at different times. And it will get transiting planets around brighter stars. And those transiting planets around bright stars can be looked at by other telescopes, such as the James Webb Telescope, which NASA is planning to launch in 2018, so that we can get more information about the atmosphere by looking at how light passes through the atmosphere on its way to us. And we want the bright stars to get enough light because the atmosphere is very thin. Then, also by analyzing Kepler data and follow-up observations from the ground in some cases, we're measuring the mass of some of these planets that we know the size of. And from that, we're going to be able to tell whether they're dense enough to be rocky. And what we're finding for planets close in, hot ones, they can be about 1.5 times the size of Earth and still be rocky. But bigger than that, they have substantial amounts of things lighter than rock. So if they have any rocky surface at all, it's under huge amounts of pressure, incredibly hot, even if they're far from their star. We're going to get more information on that from more analysis of the Kepler data, from additional data from other transiting spacecraft looking at these planets to see these little changes in their orbital period from the perturbations of their neighbors, so we can measure the masses of their neighbors that way, and also from the ground, where we, by looking at the spectrum of the star and how it varies, we can see how the planet pulls the star back and forth.
I think to the general public, one of the reasons why all of this research is so interesting is because it draws on the question of, are we alone? And I'm wondering, given that this is just sort of preliminary information, Kepler, I think, was launched in 2009, so we've only begun to get information about this field of science. But in terms of probabilistically, from your perspective, how does this data that you've looked at change the way you think about the question of, are we alone?
Well, there are several aspects to the question, are we alone, in a scientific, investigative sense. And some of them are astronomical / planetary, and some of them are biological. And we have one example of the formation of life on Earth.
Us. And everything else.
And everything else,
yeah.
Because they're all our relatives.
Yeah.
From the bacteria to the fungi to the plants, we're all related. So we don't know whether this is really rare, really difficult, and we don't really have yet a very good theory on the formation of life. We know some aspects of it, but in terms of biology, I'm no expert. In terms of planetary sciences, I think there are habitable planets in the sense of, if you put bacteria on them, simple life, or maybe a little bit more complicated than simple life, then it can grow and flourish. Whether it would evolve as far as it's done on Earth, that I don't know, because again, that's biological questions. And in terms of how many planets there are like that, well, there are hundreds of billions of stars in our galaxy. And if we look at our understanding of how many planets of different sizes at different distances from their stars, the typical star has at least one planet, on average at least. Now, most of those planets, the vast majority, are not going to be suitable for life as we know it, because we are, ourselves and our cousins on Earth, need liquid water. So it can't be too hot, it can't be too cold, it can't be too little pressure, it can't be really too much pressure either. And for that, we're talking about a tiny minority of the planets, but a tiny minority of hundreds of billions is probably still many millions, if not even a few billion.
Incredible. I was talking to some friends about the fact that I was going to be talking to you, and they made me promise that I would bring up a subject that I also think is generally interesting to the general public, which is the Fermi Paradox and the Great Filter. And the question's more I guess philosophical in nature, but the idea that if these numbers, as you're talking about, are correct, and I'm sure they are, that there are probably so many millions of planets that are similar to Earth, that we haven't been able to hear anything from them, from SETI and other attempts to try to learn if we're alone and communicate with extraterrestrials. The idea being that potentially it may be that complex life gets to a point where it self-destructs or runs into some sort of an issue where the biological experiment of life evolving goes away. Just as a speculation or getting your own personal thoughts on that matter, do you have a personal theory on why it is that we haven't come in contact or been able to communicate thus far from our experiments to communicate with other life?
I think that Fermi pointed out a very interesting issue, because if you have aliens and they're an interstellar civilization, they could expand around our galaxy. It might take them hundreds of millions of years, but hundreds of millions of years, well, they could have existed for billions or even close to 10 billion years, probably. And the fact that we don't see them means they're either hiding themselves pretty well, or there aren't that many of them, or they haven't gone out. Now, we think of going out and settling because that's a human condition. We want to explore, we want to discover new things, and we're a very expansionistic society. The United States manifests destiny. Now, it could be that civilizations that have that view don't make it to interstellar. Although I look at what you have to get to make it as far as we have gotten. And you don't just need the beginning of life, and we're not sure of that, but you need the transition of life from very simple microbes to less simple microbes. The type cells we have that have nuclei are 1,000 times as big as bacterial cells. And then going on up to animals. Very complicated steps. So getting as far as animals seems like a major challenge, even if there are hundreds of millions of habitable planets out there. Getting from animals to beings that are cognizant and controlling of their environment, I don't think is actually as difficult a step. And I don't think getting through the barrier of technology and destroying themselves is that difficult a barrier. I'm not saying that most civilizations wouldn't do that, but I can't imagine that we're talking about 99.99, etc. And remember, even if a civilization destroyed itself, is it going to cause extinction of all advanced life such that you don't have another civilization arising on the planet? To me, that doesn't seem that realistic. And we can tell that there were no advanced civilizations before humans developed. I mean, they're nothing that has left all sorts of artifacts.
So is it your view that it's just that unlikely, the evolution of sentient beings in a place as habitable as Earth is just that unlikely that we may very well be alone, or are you more of the view that there probably are many other sort of self-aware sentient beings throughout the universe?
Well, it's really technological civilizations that we're talking about. And for the most part, we're talking about the galaxy. Because going beyond the galaxy, and there are 100 billion galaxies out there too, it's a much bigger leap than becoming an interstellar civilization. And there are just so many places you can go within our galaxy. It's not clear you'd want to go out and that we'd be colonized from somewhere else. So in terms of advanced technological civilizations, there's no evidence that somebody decided to colonize everything. Now, there are hypotheses that they're observing us as like a zoo, or that we're a biological experiment, or maybe not an experiment, but just looking at the natural process. And they wait till civilizations reach a certain point and then invite them into the club if they are suitable. I don't know. That seems a lot like human morality, human perspectives. And I think that the views of space aliens are too human-centric, too like humans. So I'm not giving you a strong opinion in one direction or another. I'm just touching around the issue on things where I think I can say something. Fair.
Last question I want to ask you. I view a lot of the work that you do as sort of changing the paradigm perspective of humanity about itself. You look at sort of the landmark changes in where we are in the universe, what the Earth is. We are rotating around the sun rather than the other way around. Darwin explaining where we come from, how we evolve. And now with the more we're learning about space, that we're kind of floating around on what may be a fairly ordinary planet circulating a fairly ordinary sun. For the perspective of just the general public, what is your general takeaway in terms of how that information should change the way one views oneself and the way one views our peers and our civilization generally?
Well, I think one can view the universe with awe, but we're very isolated from other things. And most planets are not like Earth, and getting to a planet like Earth is well nigh impossible. Not that people can't do it in small numbers in a few hundred years, but we should be taking better care of our home planet.
And perhaps that perspective brings that point home, and that may be one of the great lessons that people should take away from that information, which is we're a long way from anywhere else that can take care of us. This is what we have.
Well put.
Jack, thanks so much for coming on the show.
My pleasure, Dan.
Thanks for listening. If you're interested in learning more about The Exchange, want to listen to episodes online, or would like to reach out to the show, feel free to visit the show's website at theexchangeshow.com.